Welcome to the Oblivious Transfer session. There will be 4 talks. There is track switching break after the second talk. The first talk is Reverse Firewalls for Oblivious Transfer Extension and Applications to Zero Knowledge by Subhradip Chakraborty, Chaya Ganesh, and Pratik Sarkar, and Chaya will be giving the talk.
Thank you, Nacho. Good afternoon, everybody. I'm going to talk about reverse firewalls for Oblivious Transfer Extension and Applications to Zero Knowledge. This is joint work with Subhradip Chakraborty and Pratik Sarkar. So let's begin by looking at secure computation in the classical setting. So here we have 2 parties, Alice and Bob, trying to compute a function on their inputs x1 and x2. If they run a classical secure 2-party computation protocol, they are going to exchange certain messages, at the end of which Alice and Bob learn f of x1, x2. Consider that Alice is corrupt here and Bob is honest, and the security guarantee is that corrupt Alice will not learn anything about Bob's input beyond what she can infer from the output itself. However, note that this guarantee is under the assumption that the honest party's machine is implementing the protocol correctly. That is, Bob's computer implements the prescribed protocol. So we ask what happens to secure computation in the real world where an adversary can tamper with the implementation of an honest party. So here, if Bob's machine is tampered with, it could simply leak certain keys or in fact even input of Bob to Alice, and now there is no security when Alice is malicious and Bob is honest but the machine is tampered. This kind of leakage is called exfiltration, and the question we ask in this work is, can we design protocols that give us some meaningful notion of security in the presence of malicious parties as usual, but in addition when the honest parties' machines are also tampered with. So in general, there is nothing much we can do about it in the presence of arbitrary tamperings, because a tampered machine can simply reveal an honest party's input in the clear instead of sending a valid first round message. But if we make some assumptions about the model and consider a weaker class of tamperings, we can indeed get positive results. So the model that we work with is what is called the cryptographic reverse firewall framework, which was introduced by Mironov and Stephens-Davidovitz in Eurocrypt 2015. Here we think of a machine that we call a reverse firewall that sits between the honest party and the outside world and sort of sanitizes the messages that are incoming and outgoing from the honest party. So here again, when Bob is honest, Alice is corrupt, and the honest party's machine is tampered with, if the machine simply reveals certain keys, then the firewall is going to sanitize them into innocent-looking machines when it is sent out. So we note that the reverse firewall is not trusted in the sense that we do not move secrets of the party to the reverse firewall. Instead, it is restricted to just retain its own state. It can toss random coins and acts only on the transcripts of the protocol. So it intercepts incoming and outgoing messages, re-randomizes them, but does not hold any of the party's secrets. So the properties that we expect from a reverse firewall is, first, it should be functionality preserving. So if there is no tampering at all, then it must preserve the original protocol's functionality. So even if we deploy an untampered implementation with the reverse firewall, it should not destroy the underlying functionality. And the second is about security, which is the kind of exfiltration we saw in the previous slide. That should be prevented when we deploy a firewall. We can also ask for security preservation, which says that if the underlying protocol gives us some security guarantees, then the protocol that is composed with the reverse firewall should also provide the same security guarantees. Another desirable property is what is called transparency, where we ask that the transcript messages that come out of the reverse firewall after re-randomization look indistinguishable from the ones generated by the honest implementation of the original protocol. So this kind of transparency allows us to be oblivious of the deployment of a firewall, and in particular, you can stack one firewall on top of another. So some prior related works here is the first work by Mironov and Stephens-Davidovitz that proposed the definition of a reverse firewall, and in addition, they also gave constructions for a 2-party secure computation protocol in the presence of passive adversaries. The feasibility of multi-party computation in the presence of tampered machines was shown by the work of CDN20, where they construct a reverse firewall for general MPC in the presence of active corruptions. And more recently, the work of CGPS in 21 constructed a reverse firewall for general MPC in the presence of adaptive corruptions. So both of these last two works for general MPC share a similar template. They are basically compilers that are GMW-like, that start with an underlying semi-honest protocol and constructs reverse firewall friendly sub-protocols like augmented coin tossing and zero knowledge, and perform GMW-like steps on these reverse firewall friendly protocols in order to obtain a protocol that is secure in the presence of tampering. And all of these protocols, because they are generic compilers, the reverse firewall needs to re-randomize the transcript, which means that all the underlying building blocks need to satisfy some kind of homomorphism. So the question we ask is, can we have RF-friendly protocols where the number of public key operations is independent of the circuit size, and yet somehow the protocol is amenable to re-randomization by the firewall? So we obtained the following results. First, we show a reverse firewall-friendly OT extension protocol based on the KOS 15 OT extension protocol. In order to do this, we construct a random OT that can be used as base OTs, and we show exfiltration resistance for this random OT by constructing a reverse firewall for this. And along the way, we introduce this notion called full malleability for Sigma protocols and for interactive zero-knowledge proofs that could be of independent interest, but we use this in constructing our random OT. And finally, we show how our OT extension protocol can be used in order to obtain an exfiltration resistant zero-knowledge protocol by building on top of Quicksilver, which is a circuit zero-knowledge protocol that uses OT extension. So let us begin by looking at what Oblivious Transfer is. Oblivious Transfer is a fundamental cryptographic primitive that is used in most secure computation protocols. So here we have a sender and a receiver. The sender has two inputs, M0 and M1, and the receiver has a choice bit B. At the end of the protocol, we want the receiver to learn the secret M sub B, and the security asks that the sender does not learn about the receiver's choice bit, and the receiver should learn nothing about the other secret of the sender. There are other flavors of OT, like random OT and correlated OT. In random OT, the functionality chooses two secrets, M0, M1, and the choice bit B, and outputs these two secrets to the sender and the chosen secret to the receiver. In correlated OT, the two secrets that the sender will receive at the end of the protocol are related by a correlation delta. By a result of Impagliazzo and Rudich, we know that we cannot construct oblivious transfer in a black box way from one-way functions, which means that OTs require expensive public key operations. And given that in practice, OTs are typically used in large batches, like one OT per input bit or one OT per AND gate in the circuit, we need them to be efficient. And this brings us to the idea of Oblivious Transfer extension introduced by Beaver in '96, where we can amortize many OTs using only symmetric key operations which are cheap, and only a small number of OTs that are called base OTs. After Beaver '96, Ishai, Kilian, Nissim, and Petrang gave an efficient OT extension protocol. The template of an OT extension is as follows. There are K parallel seed OTs that are run, where K is security parameter. And after this, we run we use some symmetric key operations in order to obtain M many OTs, where M is polynomial in the security parameter. So when M is large, we get amortized cost per extended OT to be a constant number of symmetric key operations. So using K seed OTs and many inexpensive symmetric key operations, we get many OTs, extended OTs. So let us start by looking at the high-level idea of the KOS correlated OT extension, which is our starting point. So here we have a sender and a receiver. The receiver has a choice bit vector. The first phase is running the base OTs, and here the roles are reversed. The KOS sender acts as the receiver, and the KOS receiver acts as the sender in the base OTs. At the end of this step, the KOS sender receives a secret and a choice bit. So in this step, the base OT functionality is going to sample two secrets K0 and K1 for every ith base OT. And a random bit S for every ith OT. And the receiver receives the two secrets K0, K1, and the KOS sender receives the bit S together with the Sth secret. After the base OTs are done, the receiver is going to construct a choice bit matrix, where each row of this matrix R is a monochrome vector consisting of the jth choice bit. And now it prepares two different matrices, a matrix M, where each column of the M matrix is obtained by applying the PRG on the 0th secret, and a matrix D, where each column of D is obtained by XORing the choice bit vector R and the PRG applied on both secrets that it received at the end of the base OT protocol. This matrix D is sent over to the sender of the extension protocol, and given this, the sender can compute a matrix Q such that each column vector of this matrix Q is given by, so this is component-wise multiplication here. So we have that it is the choice bit component-wise multiplied with the ith column of D XORed with PRG applied on the secret that it obtained as the receiver in the base OT protocol. So here, if the sender outputs SNQ and the receiver outputs R and M, we see that this is indeed the output we wanted from the correlated OT. So the rows of Q and the rows of M are correlated this way. Now, if we think about exfiltration resistance in this protocol, so in order to make this maliciously secure in the presence of a malicious receiver, a bad receiver can choose the choice bit matrix in a different way. In particular, it need not be monochrome rows. We have to add some consistency checks in order to force the receiver to actually use the correct choice bit matrix R. Now, if we think about how to construct a reverse firewall for this, let us look at what steps in this protocol can actually leak in the presence of a tampered implementation. So first, it could be that the base OTs are itself not exfiltration resistant. It could leak secrets. So this should be exfiltration resistant in order for the OT extension protocol to be exfiltration resistant. And second, we have to worry about this matrix D that the receiver sends. That could be either leaky, or a malicious receiver could trigger a tampered sender by sending a bad, not well-formed D. And third, the consistency checks must also be exfiltration resistant. So let us begin by looking at the base OT protocols and how to construct a base OT protocol that is friendly to construct a reverse firewall. So here our starting point is the protocol of Bellare and Micali. So here we have a sender and a receiver with a choice bit B. The sender samples a random Q and sends G to the Q to the receiver. The receiver samples two public keys, PK0, PK1, such that PK sub B, where B is the choice bit, is G to the SK for a known secret key SK. And then it sets the other public key to be Q divided by the public by PKB and sends PK0 to the sender. Now the sender samples some random paths R0 and R1 and sends G to the 0, G to the R1. And now both of them can compute PK0 to the R0, PK1 to the R1 are the two secrets that the sender outputs, and RB to the SK is the secret that the receiver outputs. In order to make this maliciously secure, we need to extract from the corrupt party. So in order to do this, we add some additional steps to this protocol, where after the first step where the sender sends G to the Q, we also ask for an interactive proof of knowledge where the prover proves in zero knowledge of the exponent little q such that capital Q is G to the Q. And now the simulator can extract little q from this proof and simulate. When the receiver is corrupt, we again need a proof of knowledge of the exponent for the public keys. So here we have a witness indistinguishable proof of knowledge of SK such that either PK0 is G to the SK or PK1 is G to the SK. So this is our base OT protocol. And now if we think about exfiltration resistance of this protocol, at a high level, we have that we'll have to take care of three different things where secrets can leak. For instance, if the sender is corrupt and the receiver is tampered with, then a bad first message from the sender could trigger the receiver into leaking some secrets. A tampered receiver could also leak secrets through the public keys that is sent. And finally, the pads that the sender sends as the final message could also be ill-formed. So in order to handle this, we first replace the first phase of the protocol where capital Q is sent by the sender by doing a kind of coin tossing where the receiver first commits to QR, where QR is G to the R for a randomly sampled R. And then the sender sends its contribution to Q, we call that QS now, together with the proof of knowledge. And then we'll have the receiver decommit, and both of them set Q to be the product of QR and QS. So this is now a coin tossing phase, and why is this helpful? Because now this becomes amenable to re-randomization. So if we have a reverse firewall here, and if we assume that these commitments are homomorphic, then the reverse firewall can re-randomize this. We also need to re-randomize the proof of knowledge, so we are going to need something that I'll call fully malleable zero-knowledge proof of knowledge. I'll say what that is in a bit. But assuming homomorphic commitments and a fully malleable proof of knowledge, we can now re-randomize this coin tossing phase using a firewall. Finally, coming to the public keys sent by the receiver, again, we don't want this to be ill-formed, and therefore, we will have a contribution from the sender. So the sender commits to a field element P. The receiver now sends PK0 together with a proof of knowledge, a witness indistinguishable proof of knowledge. The sender then decommits to P, and both of them redefine their public keys, PK0 prime and PK1 prime, to include G to the P, while maintaining the invariant that the product of the two public keys is capital Q. So this is the re-randomizing of receiver public keys phase. And again, this is helpful because now we can have a reverse firewall that can take advantage of this homomorphic commitment scheme. And assuming that this witness indistinguishable proof is also malleable, the reverse firewall can indeed sanitize this. Now for the last message from the sender, which are these random pads, we again want the receiver now to commit to two pads V0, V1. Then the sender sends its two pads, the receiver decommits, and now both of them can redefine the pads to be R times G to the V, and using R prime and SK prime, and using R0, V0, and R0, V1, we still maintain correctness of this OT protocol. So the three phases we have is obtain Q via coin tossing, re-randomizing of the receiver public keys, and re-randomization of the sender messages. So if we use, again, homomorphic commitments here, the reverse firewall can maintain correctness while re-randomizing these messages. So however, the base OT that we need for our extended OT protocol needs to be a random OT, and therefore we want to also re-randomize the choice bit. So in order to re-randomize the choice bit, we'll have the sender send a random bit row. And now the firewall can randomize this to row hat by picking a random row tilde. And now if row tilde is 1, then the receiver's choice bit is flipped, and therefore the firewall also has to permute the two public keys PK0 and PK1 in order to maintain correctness of this protocol. And this is something our firewall can do using the fully malleable proof of knowledge. So I'll just say a little bit about our fully malleable protocols. Let's illustrate this using Schnorr's protocol for discrete logarithm, where the prover is proving knowledge of discrete logarithm of a public group element. So in Schnorr's protocol, the first message from the prover is G to the R for a random R. The verifier sends a random challenge C from ZQ, and then the prover responds with a third message Z, which is R plus CW, a function of the witness and the randomness of the first message. Now the observation is that this protocol is re-randomizable so that it yields an accepting transcript without knowing the witness if the underlying transcript was also accepting. This is what we call the full malleability of Schnorr's protocol. And here we also want to re-randomize the instance, because when we use this as a building block in our OT, the instance can also be subliminal and tampered with, and therefore we want to sanitize this. So the prover sends both the instance and the first message of Schnorr. And the reverse firewall is going to pick randomizers, delta for the instance, rho for the challenge, and gamma for the commitment, and re-randomize all the messages. So I'm running out of time, but hopefully it's clear that with this re-randomization, if the original transcript was accepting, that is, if X, A, C hat, and Z was an accepting transcript for proof of discrete log, then after re-randomization, we still have an accepting transcript. So full malleability says that it admits algorithms small and balance, such that when they're applied on the messages of the prover, we obtain an accepting transcript, and this is also exfiltration resistant. So this notion of full malleability is different from malleable sigma protocols in literature, in that the sanitized transcript was for the same instance in existing work, whereas we also have to sanitize the instance. So in the paper, we construct a reverse firewall for the full zero-knowledge protocol compiled from Sigma protocol. Here we take advantage of the key homomorphism and message homomorphism of the Peterson commitment scheme in order to randomize the commitment key, the commitment, and the message inside the commitment. We also construct a reverse firewall for the OR transform of Sigma protocols, and this is what we use for our witness indistinguishable proof in the base OT. So this is our final base OT protocol that provides, that admits a reverse firewall and provides exfiltration resistance.
So, I mean, we are almost out of time.
I'll stop in 30 seconds. So this is the random OT we use here. We also have to take care of other concerns, which is exfiltration via the matrix D and the consistency checks. So here we need some new ideas in order to generate D via coin tossing and have the receiver commit to D and open D together with its response to the consistency check in order to prevent exfiltration. The details are in the paper. And I am going to stop here with so we finally use this OT extension to give a version of Quicksilver, where the prover computes authenticated values of wires in the circuit, and for each multiplication gate proves correct relationship. And we can make this exfiltration resistant by using our exfiltration resistant correlated OT in the first phase of the Quicksilver protocol. I'll stop here, and I'm happy to take questions.
Thank you. If someone has a quick question, please go to the microphone. And otherwise, just for interest of time, maybe we can go to the next talk. Let's thank Chaya again. The next talk is Oblivious Transfer with constant computational overhead. This is by Elette Boyle, Geoffrey Couteau, Niv Gilboa, Yuval Ishai, Lisa Cole, Nicolas Reich, and Peter Scholl. And Nicolas is going to give the talk.
Great. Thank you very much for the introduction. All right, so this work and this presentation is concerned with the concept of computational overhead. So what do I mean here? Let's consider some sort of computational task which has some original cost n. So a nice motivating example you can think of is evaluating a circuit of size n. And then oftentimes in cryptography, we sprinkle some, you apply some cryptographic compiler and somehow transform this original computational task into some sort of secure realization of it. So maybe you want to do this, evaluate the circuit with like two non-trusting parties who share the inputs in the case of two-party computation. And now many of these sort of compilers that you run into in practice, they have the following sort of property. If we look at the new cost of running this, this task securely, the new cost will usually scale, well in the best case it'll scale linearly in n, but usually the constant in front of this linear term will somehow grow with the security parameter. So maybe it costs 10 times n if you want 128 bits of security, but when you want 256 bits of security, maybe it would be 20 times n, or 40 times n when you want 512 bits of security. And maybe it's reasonable to ask, well, is this inherent? Could we somehow get security costs, we could get a cost which is somehow independent of the security level? If you reflect, maybe this seems a bit unreasonable. Maybe you have to protect each step in some way, so you should have some cost which depends on the security parameter. But it turns out that actually for many natural tasks, it was already shown by Yishai, Kushelevitz, Ostrovsky, and Sahai in 2008 that we can have constant computational overhead for things like encryption, signatures, and actually most relevantly for this talk, so the one I would like to focus on, the case of semi-honest two-party computation. All right, so allow me to just set the stage here. I guess a lot of what I'm going to say now might be repeated from the previous talk, but bear with me. So in two-party computation, we have two parties, Alice and Bob, with private inputs x and y, and they're allowed to communicate back and forth in such a way that at the end, they will know the output value of a certain function applied to both their private inputs. So say this function f is implemented by a circuit, and we'd like to evaluate the value of this function in such a way that nothing beyond what can be inferred from the output of the function is learned by the other party. So maybe Bob at the end of the protocol will learn that, x is greater than y if the function f evaluates, is x bigger than y, but he won't know by how much larger x is than y. Okay, and for semi-honest security, this is sort of a nicer model where we assume the parties follow the protocol, but we can also consider a more annoying model of malicious security where the parties might deviate from the protocol. So maybe in one step, Alice is supposed to send a random bit, but she wants to, learn as much as she can about Bob's input, so she'll always send 1 just to try to, infer as much as she can. Okay, so allow me to say a little bit about the history of constant overhead for two-party computation, just to set the stage. So I've already mentioned this result by ICOS in 2008, which achieves semi-honest security, and it works for evaluation of Boolean circuits with constant computation and communication overhead. So this is great. But now you could, ask for malicious security, and that's what we'll be interested in today. So in sort of an orthogonal direction, we could replace the task of evaluating a Boolean circuit with, say, evaluating an arithmetic circuit over a field of size 2 to the lambda. So in some sense, your arithmetic operations are already kind of encoding the size of the security level that you're dealing with. But in this model, it is indeed possible to have constant computation and communication overhead. But now, if you really insist on malicious security in Boolean fields, unfortunately, the current state of the art is a little lacking. The best computational overhead is still quite impressive, but it's polylogarithmic, so not constant. Okay? Now, I'd also like to mention some other works which achieve, in some sense, worse computation. It's actually the best results right now achieve sort of polynomial and then computational overhead. But the communication, I'll point out, is actually sublinear in n, so that's kind of interesting. And this line of work is based on so-called pseudo-random correlation generators. And part of the main reason I wanted to introduce this bottom row of this table here is because this is the sort of framework that our result fits into. Now, I would like to be able to stand here and say, OK, we get the result where, I have greens in all the entries, and so we're done here. Unfortunately, I can't stand here and say that, but I can stand here and say that we make progress on what we think is a natural step towards this goal. And that's we're going to focus specifically on the task of generating n-bit OTs. Okay, so I'll define OTs in a second. I guess many in the audience have already seen it from the previous talk, but bearing with me for a second, why is this sort of an interesting computational task? Why should you care? Well, I'll point out first of all that this is known to be complete for semi-honest two-party computation. Okay, well, that's maybe not so impressive because we care about the malicious setting here, but in some sense, this completeness result partially extends to the malicious setting. So at the very least, if you have a way of generating bit OTs with malicious security, that will still give you some sort of nice security for general two-party computation. Essentially, you can get security up to some sort of additive attacks. We also have some other comments about how this gives nice results for if you want to compute the same finite functionality, n times, or you can somehow reduce the open questions that we have to conceivably simpler ones. Perhaps as a more philosophical level, I'd like to argue that it's a good benchmark for techniques, and maybe the best way to see this is just by looking at history. Many past research efforts have been implicitly studying this question, sometimes under batch OT or OT extensions we saw in the previous talk. So this is sort of a nice way for us to get a handle on, how well are we performing with the MPC techniques that we've developed. All right, so allow me to quickly introduce the bit OT functionality. Hopefully it's familiar to many in the audience, especially if you were just in the previous talk. So Alice has some choice bit B, which she can enter into this, magic OT box. Bob can then input 2 messages, M0 and M1, and at the end, Alice will learn some message MB that she selected, but not the other message. And also, Bob doesn't learn which message Alice received. And now, in fact, I guess similar to the last talk as well, we will mostly be concerned with the case of random oblivious transfers, where instead of Alice and Bob picking B, M0, and M1, they're just randomly selected by the functionality. That is usually what we need for implementing most 2PC protocols. Good, so without any further ado, allow me to state our main contribution. So we need to make a few assumptions. The first assumption is, okay, we need there to exist at least one OT protocol if we're going to create n OTs. So let's make that minimal assumption. The next assumption, I won't be able to say too much about where it comes in, other than very briefly, but we make a certain learning parity with noise assumption, specifically an Alknovich style assumption, assuming that it's even hard if the corresponding matrix is very sparse. But I'll leave that a bit vague. The last assumption, which I'll say a bit more about, is that we need to have a pseudorandom generator, which has a very nice locality property. I'll explain what that is later. And we also need some technical correlation robustness notion, which we sort of argue is pretty minor. Good. With these assumptions in place, we can get a two-party protocol for realizing n instances of bit OT with the desired computation costs. So if you think of capital N as being, sufficiently large polynomial in the security parameter, the computational cost will be like some constant times n, independent of whatever security parameter lambda that you've chosen. And also, just, which is kind of a nice bonus, not even something we were aiming for necessarily, since we're relying on this PCG framework, we get sublinear communication costs. So I'll mention that, for example, the IKOS protocol does not achieve sublinear communication as we do. Good. So as I say, our line of work builds on a pseudorandom correlation generator. So allow me to quickly define these. So I would like you to think of them as some, again, I just like having these sorts of boxes for, denoting functionalities. So again, a pseudorandom correlation generator is some sort of functionality which now outputs short seeds, SA and SB, to Alice and Bob. And the nice thing about these seeds is that Alice and Bob can then apply some sort of expansion algorithm, so I just note expand here, and convert their seeds into some sort of longer strings. So this is, first of all, it's just like a pseudorandom generator. We still have that property that if I take my short seed and I run this expansion process on the seed, then I'll get what looks like a pseudorandom string. Also, I should emphasize here that this expansion step requires no communication from the parties. This is just local computation that they can do on their own private machines. But amazingly, since the seeds were correlated when they were output, the expanded strings, so this green vector for Alice and this orange vector for Bob, they will have the property that they satisfy some useful, correlation, let's say. Maybe we get n independent OTs. That would be sort of, what we're targeting here. And lastly, of course, we need some notion of security because, this is two-party computation, so Alice and Bob don't necessarily trust each other. This is very informal. The precise definition requires a bit more work, but informally, the other party's output should just look pseudorandom up to the fact that I know, okay, well, we created a whole bunch of bit OTs, so it better satisfy that correlation. And now I can just quickly point out that basically to go from this result on a construction of a PCG to some sort of maliciously secure 2PC protocol, we just kind of replace the functionality with an appropriately efficient, maliciously secure 2PC protocol from the literature. So we use one from Ishai, Prabhakaran, and Sahai from 2008. Okay? So in fact, it's fair to say that our main result is actually a construction of a pseudorandom correlation generator. We make these two assumptions now that we have, this LPN assumption and this correlation robust local PRG. Then we are able to construct a PCG for realizing n instances of bit OT. And the main sort of effort, a lot of the work that we had to put into this construction was getting this expansion phase computation cost down to being linear in n, like this. So this is how we end up getting the constant computational overhead in the resulting 2PC protocol. And also just, this kind of usually get this in any sort of non-trivial PCG construction, you'll get sublinear seed size. So these are sort of this is sort of the main result that, that we have to offer. And in my remaining time, I guess I have 6 minutes, leaving time for questions. I'm just going to do my best to give you a flavor of the sort of ingredients which go into our construction. Okay, so this first ingredient here, this PCG for non-independent OT-like correlation C. Okay, this is, a lot of hand waving here. But you can think of this as some sort of box that we implement, which spits out kind of a vector to Alice and Bob, which kind of look like, n OTs. But the problem is that, maybe the first OT is correlated with the second OT, and the second OT is correlated with the third OT, and all these sorts of correlations appear. So this is the first step. And this kind of pushes some techniques which I guess have been sort of exploited in this recent line of works on PCGs. I guess the original idea maybe is Boyle, Couteau, Gilboa, and Ishai. Maybe it was earlier as well. Maybe someone can correct me in the audience. But here we use this sparse LPN assumption to have a very efficient pseudorandom generator that also has nice linearity properties. And this linearity property will interact nicely with what I'm calling succinct additive sharings of structured vectors. In the literature, this is typically called function secret sharing, if this concept rings a bell. But in any case, I'm not going to have time to really say too much about this part of the construction here. I'm going to focus more on the second step, where we use our local pseudorandom generator in order to sort of break the correlations that we have from this box C, which we've implemented. Okay, and this idea is sort of inspired by what ICOS did in 2008. Good, so here's what we have at the moment. Let's say we've somehow implemented this, this sort of box which outputs, n long vectors of a whole lot of coordinates, and they all sort of look like OTs, but they're not exactly. And in fact, they'll be sort of these kappa long vectors. So this is the sort of structure that we will have. And now we can use like the original idea for dealing with this dates back to Ishai, Kilian, Nissim, and Petrank from 2003. They suggest, well, it might be the case that this first coordinate is somehow correlated with the second coordinate, and so on and so forth, but we can break these correlations if we have access to what is called a correlation robust hash function. Okay, so we just sort of use this hash function in such a way that at the end of this we get out a whole bunch of bit OTs as we wanted. So this is great. It does indeed work. It'll give you n independent bit OTs, but there's a bit of a problem here given our goal. So if you think for a second, you'll need kappa to be, it needs to be at least the security parameter if we want the correlation robust hash function to have, the desired notion of security that we need. Of course, I haven't really defined the security notion carefully enough, but it's quite easy to see that if the security parameter, if the kappa here is not larger than the security parameter, we won't be able to guarantee the security of the pseudorandom correlation generator. So we need to work a bit harder. So what can we do instead? Instead, we're going to try using a local PRG to solve our problems. So how does a local PRG work? You can think here of this as this top vector here is the input, like the short seed of it'll have length kappa, matching what was on the previous slide. And a local PRG behaves as follows. It sort of reads off different subsets of bits, kind of one at a time. So say, I read off here 5 bits, or I guess the parameter I'll use is L, but read off 5 bits from the input, then another 5 bits from the inputs, and I do this, say, capital N times, or maybe not capital N. I do this, a whole bunch of times to create all of my one for each output bit. And to each of these subsets here, I apply some carefully chosen predicate. I mean, there's a lot of work that goes into picking the right predicate to use, but some way of mapping, say my small number of like 5 bits here down to 1 bit. And then when I apply this predicate, I get these purple bits out. And the idea is that if you choose this predicate carefully and these subsets are not too, they have some nice expansion properties, this should give you a local PRG. Okay? And now denoting sort of the function which, say, selects, the coordinates that the ith output depends on by pi I, the idea will be to, instead of using the h each time, for the ith application of the hash function h, we'll replace it by, say, first I'll read off some L coordinates depending on, pi sub I, and then just apply this one predicate. So this is somehow now like a computation which only depends on L bits rather than on kappa. So we could hope to, have some sort of constant size computational overhead for each step. I should also mention that the idea of a local PRG dates back to Goldreich in 2000. It's been a very well studied, assumption for many years now. There are lots of interesting works about how to construct these things and what sort of stretch you can hope for. Okay, so just to finalize the last idea of this construction, so we could, just go from this sort of correlation here, and instead of, applying h, we apply, say, p composed with pi sub I. Still doesn't quite work though, because, I needed to share, kappa times n things all at once, so sort of, I'm kind of creating too much material, but in some sense we've created more material than we need, because in order to figure out the ith output, I only need, say, the coordinates of each of these vectors here that, pi sub I picks out. So this is how I tried to denote it by, like, these, we only pick out the specific coordinates that we actually need, and that's the only thing that we have to share. Now this, so now we think of there being only L per column, and we just have to apply the predicate P. This does sort of put more challenges on the, say, the sharing schemes that we need to construct in order to implement the PCG for this new sort of projected correlation. This is indeed one of the things that require quite a bit of work, but suffice to say, sort of the same ideas which I'd constructed previous PCGs can sort of be applied in a careful way to derive this sort of construction. Okay, good. Allow me just to very quickly give some sense of the concrete efficiency estimates. So in fact, we give two constructions depending on the flavor of the learning parodies with noise assumption that we use. And we have a primal construction where it seems like at the moment we could say have roughly 300 operations per OT, independent of the level of security. We also provide a dual construction based on some what we call repeat accumulate codes. And these, seem to allow for slightly more efficient operations, about 100 operations per OT. Okay. However, I should perhaps stress here that I'm not claiming that this is actually concretely practical at the moment. I mean, this is sort of still just kind of a theoretical proof of concept that it is indeed possible to generate such, OTs with constant computational overhead, even in the malicious setting. Getting, practically efficient protocols is indeed an interesting future direction, I would say. All right, allow me to quickly recap. So we talked about today these bit OTs. This is the OT Oblivious Transfer session. And one of the main ideas that we used to get a result was a construction of a PCG, where I'll remind you, we have short correlated seeds that get expanded in some sort of silent expansion phase into pseudorandom strings that satisfy a target correlation. We needed to use this local PRG in order to have sort of constant overhead per output of the PCG in the expansion phase. And then we had this idea of, constructing sort of this projected version of the correlation in order to reduce the computational overhead per step. All right, that's all I have time for, I think, so I'll stop here and take questions. Thank you.
Any questions? About the estimates that you had at the end, these are asymptotical, no? The 300 per OT, meaning that, say, it's supposed to hold if you have like, if you want to generate many OTs. Do you have any numbers where it could be in that ballpark of 300?
Oh, yeah. Okay. I do think the dependence of the number n will have to be polynomially larger than lambda, but a big polynomial that I'm probably embarrassed to say out loud. So I don't know if I can really give, I don't know if I'm confident in saying anything like
okay.
that. Yeah, I remember working out at some point and it was not pretty. Yeah.
Okay.
What kind of operations? 100 operations?
Oh, yes. Yes, good. So the model that we use is we just say any gate that takes 2 bits and outputs 1 bit is one operation. So I could do a XOR, I could do an AND, I could do a not AND. Yeah. So they're all binary operations. Perhaps I really should have emphasized that point. Yeah, Boolean binary operations.
Okay, let's thank the speaker again. And now you have like 8 minutes to switch tracks if you want. Yeah. Yes, you are the speaker now. Yeah.